Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in CSE in Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about the importance of graphs. So, a graph is nothing but knowing a data structure. So, in tree structure, there should be a hierarchical representation between the parent and child, and that means one parent and no children. On the other hand, in graph, a relationship is from many parents to many children. So if I'm going to define a graph, so a graph is nothing but a set of vertices and edges, and this set V is nothing but set of vertices and nodes, and V is nothing but set of edges connecting the vertices, and edge UV should be a pair of vertices. So example, if I'm going to consider, so V is equal to ABCDE and V is equal to ABCADE, CDCE and then D. Right? So here what I'm going to say that is, so the graph is nothing but a set of vertices or nodes, and E is nothing but the set of edges that is going to be connecting the vertices, and then edge E is nothing but UV should be the pair of vertices. So V is equal to set of vertices and V is nothing but the set of edges. So consider a graph terminology. So here what I'm going to say, I'm going to consider a diagram. A diagram is nothing but a diagonal graph. So in graphs, we are going to be considered where V should be set of vertices and V should be set of pair of edges. And the edge is going to have the directions. And the graph is going to be ABCD, and the edges I'm going to consider ABAC, AD and E. So there are two types of diagonal graphs. So G is nothing but diagonal graph. So if the edge is going to be an ordered phase, an undirected graph, so the edge is nothing but the unordered phase. Okay. So whenever the graph is going to have the directed edges, then it should be called as a directed graph. And whenever the edges is not going to have any kind of directions on this, then it should be called as an undirected graph. And we're going to see some of the terminology like simple path. So what should be the simple path? So the simple path is the path where the vertex is not going to be repeated twice. Okay, so that should be the path of the term. So if I'm going to consider this, so it is the path A, B, E, C, D, and then AC. So this should be the graph. So A, B, D, CD and D. So that should be the simple path. If I'm going to answer the question, then should not be a simple path. And B, E, C should be also a path here. And cycle means that, so whenever the starting vertex and then ending vertex is same, then I can easily say that should be a cycle. So this should be the cycle. So parallel edges means that whenever the graph is going to maintain two or more edges between the pair of vertices, then it should be called as a parallel edge. So see some of the different types of graphs. So cyclic graph means where the graph contains the cycle, then it should be called as a cyclic graph. And where the graph does not contain any kind of cycle, so then it should be called as a acyclic. So there is no cycle here, so here also no cycle here. And weighted graph means that whenever the edge is going to carry the weights among the edges, then it should be called as the weighted graph. Okay, so a graph which is going to hold the vertices, edges among the weight, then it should be called as the weighted graph. And the complete graph is that so a graph which is going to hold vertex to every other vertex, then it should be a complete graph. That means that there should be edges and edge between every pair of vertices A, B, A, C, A, D, and A, E. Then it should be called as a complete graph. And the strongly connected graph means that So whenever there exists an edge between the pair of vertices, then it should be called as a strongly connected graph. So let us consider this. So D to A, A to B, and then B to D, and B to D, B to C, and B to C. So strongly connected graph means that, so whenever there is an edge between the pair of vertices, then it should be a strongly connected, and complete graph means that, so there should be an edge between for every pair of vertices. So similarly, I'm going to consider B here, from one edge from every pair of vertices. Similarly, I'm going to consider E, so E to B, E to B, E to A, and E to C. I'm going to consider D to B, D to A, D to C, and D to E. So like this, we are going to be considered. So subgraph means that, so we're going to have the graph. So in this graph, I'm going to consider one vertex that should be considered as a subgraph, and 0, 1, 2 should be one subgraph, and 0, this form is also going to be subgraph, and this one is also going to be subgraph here. So some other subgraph show like this. So a subgraph is nothing but some part of the graph is nothing but a subgraph. So if I'm going to consider a graph like this, so this C, D, E should be the some part of the graph. So this one going to be treated as subgraph of this graph, and AB should also be treated as a subgraph of the graph. So graph is nothing but some particular part of this graph, or some particular vertices of the graph to be considered as subgraph. So even more terminology. So we're going to be connected to a graph. So that means that two vertices are going to be connected. That means that whenever there is an edge between the every pair of vertices, then it should be a connected graph. And not connected means that, so this as a one graph, and this one should be considered as another graph. That means where the at least two vertices are not going to be connected, then this graph is said to be a disconnected. So whenever two vertices may not be connected, then it should be considered as not connected, one should be considered as a disconnected graph. So subgraph means that, so here some of the subgraph also in the graph is mentioned here. So this is also another example of that. And next one is that simple graph. So what is a simple graph here? So simple graph means that, so a graph that does not maintain the multiple or parallel edges and then loops. So that kind of graph, what I'm going to say that is that simple graph. Okay. A simple graph is the graph where the edge does not contain the side loop and parallel edges, then I can able to say that should be the simple graph. Okay. A graph, if it does not have any loops and parallel edges, then it should be considered as a simple loops and parallel edges, then it should be a simple graph. Connected graph. So what should be the connected graph? Multigraph. So what is the multigraph here? So multigraph means that, so when the graph is going to maintain multiple edges, then you can able to say that should be the multigraph. So there are two parallel edges between A and B, and then C and D, and B, C, C, D also. So similarly, pseudograph. So what is the pseudograph here? Pseudograph means that, so whenever the graph is maintaining the self loops, so then I can able to say that graph should be the pseudograph. So these are the different types of graphs here. And what way is going to be represent the graph? So there are two ways where the graph is going to be represented. So first one is a sequential representation. So that should be a adjacency matrix, and linked-list representation by means of linked list. Okay. So sequential representation means that, means of adjacency matrix, and linked list representation is the linked list. So sequential representation is equivalent to adjacency matrix, and linked list representation is the means of linked list. So what is the adjacency matrix here? So adjacency matrix is a bit matrix. So where entries contain zeros and ones, and since it is going to store information whether the adjacency matrices are present or not. So that means that whenever there exists an edge between A and B, then I can able to store the value 1. If there is no edge that is going to be entered, then it should be 0. So this representation is a square matrix where I should be the number of vertices in the graph, and adjacency matrix are undirected graph, this should be 0. So let us construct the set of vertices and edges. So here we are going to hold the values, and that means here. So in this graph, so there is an edge. We are going to construct the set of rows and columns as the vertices, and then we have to number. So whether there is an edge from A to C, so A to C should be 1, and A to B, and A to B. So that's why it should be 1. So remaining A to A, so it's not there, and then A to E, also not there. So that's why we number the values for the A. And if I'm going to consider this B here, second one, so one of the vertices that I'm going to take connection B to A, B to C, and B to B. So B to A, B to C, and B to B. And next one C. So from C, it should be C to A, C to B, C to D. And C to D also. So C to A, C to B, C to D, and C to D. And the next one, D, I'm going to consider it. So D to A, D to B, D to C, and D to E. Then to E, I'm going to consider E to C and E to D. So the adjacency matrix is a bit matrix. So it is going to contain into zeros and ones. And since it's showing the information whether the adjacency vertices are present or not. So the connected edge between the two vertices should be represented by 1. And the absence of this edge is going to be represented by 0. So this matrix uses a square matrix and n by n. So where n should be the number of vertices in the graph. So linked list representation. So in linked list representation, we are going to save the memory first. So there is a advantage of this linked list representation. And the number of lists that should be depend on the number of vertices in the graph. Okay. So the number of lists should be depends on the number of vertices in the graph. So whenever I'm going to have any vertices or 5 vertices, so that's why I'm going to consider the 5 vertices. So the header node in each list contains the list of adjacent vertices. So if I'm going to consider 1 here, so what are the vertices that are connected to A, B, and then C, D? So B, C, and then D. So similarly, if I'm going to construct B here, so what I'm going to consider, so A, B to C, and B to D. So like this. And next one, C if I'm going to consider, so C to A, C to B, and C to D. So I'm going to consider D, D to A, D to B, and D to C. So like this, we are going to consider this linked list representation of the graph. Okay. So if I'm going to have the vertices, based on the we are going to represent the vertices as nodes. So from this, we are going to be identify what are the vertices that are connected to it. So this is under example of representing the linked list in the sensing matrix. So in the case of this undirected graph, so previous one is directed graph. So this is under example we are going to construct the sensitivity sensing matrix. So in this one, so first we are going to present the sensing matrix. So 1 to 0, 1 to 1, 1 to 0, 0, and 2 to 1, 2 to 3, 2 to 4, and 2 to 5, and 3 to 2, and 3 to 4, 4 to 2, 4 to 3, and 4 to 5, 5 to 1, 5 to 2, and 5 to 5. So how are we going to represent this? So 1 to 1, it should be 0. So 1 to 2, 1. So that means 1 to 2 and 1 to 5. So therefore both should be 1. And 2 if I'm going to consider. So 2 to 1, 2 to 4, 2 to 3, and 3, and 4, and 5. So again, we can then consider 3. So 3 to 1, and 3 to 4. So 3 to 2, and 3 to 4. 4 you can going to consider 4 to 3, 4 to 2, and 4 to 5. That means 5. That means 5 to 1, 5 to 2, 5 to 2. So next what I'm going to say that is, now this one is going to present as a linked list. So for 1 I'm going to consider, so what are the net of contact 1 5, so 2 is I'm going to consider and select it. And next one if I'm going to consider 2, so 2 means 1, 3, and then 4 and 5. So 1, 5, 3, and then 4. So you can consider 3, so 2 and then 4, so 2, 4 is going to be 4. So 2, 3, 5, so 2, 3, and then 5, and then 5, 1, 2, and then 4, 1, 4, and then 5. So in case of directed graph, so how it will be? So previously undirected graph, so that means that so the both directions is going to be considered in this case. That means so 1 to 2 is same, and 2 to 1 is also same. So 3 to 4 is same, and 4 to 3 also same. So like this. So whereas in directed graph, so the increase is going to be like this. So whenever you are going to have the direction, so that one is going to be presented as well. See here. So 1 I have only 2. So 2 and then 4. And for 2, only 1. So 2 to 5. And then for 3 I have 5 and 6. And the 4 should be 2. And 5 should be 4. And for 6 it should be 6. Okay, like this you are going to be present this adjacency matrix directly. So when it comes to adjacency list, so based on this matrix we are going to be doing this adjacency list as well. So for 1 I'm going to have 2 and then 4, and for 2 I'm going to have 5, and for 3 I'm going to have 5 and 6, and for 4 I'm going to have 2, and 5 I'm going to have 4, and 6 4 6. Okay, like this we are going to be representing adjacency list and something matrix of the directed. So if I'm going to make the comparison, so the adjacency matrix representation requires n by n matrix. So that means that if n vertices, we're going to have n number of edges. So but from manipulation point of view, this representation is the best. And in case of insertion, deletion, and searching is concerned, so the linked list representation has the advantage. So but overall performance is concerned, so the matrix representation of the graph is more powerful than. So when I'm going to compare this adjacency matrix and then adjacency list, so Simple representation of the graphs by considering number of rows and by n. So it's simple and easy to implement. So whereas when compared to this linked list, so the insertion, deletion, and searching is going to be simple, more powerful, easy. So insertion operations will be easy. And presentation of the graph is also going to be more powerful since it is going to be saves the memory also. And next we are going to see some of the graph traversals like breadth first search and depth first search. So DFS and DFS. So traversals means that we are going to be visit all the vertices in the graph exactly once. So that should be the graph traversal. And DFOs is going to be an acyclic graph. And DFOs on the same graph do not give the same order visit of vertices. And at the same time, the order of visiting nodes depend on the node where we have to be selected the first, and hence the order of visiting nodes may not be unique. Okay, so we're going to have two standard definitions, the traverses, so depth first search and the breadth first search. So traversing of the graph means that visiting all the vertices in the graph exactly once, and the breadth first search and depth first search is going to result in acyclic graph. So that means the graph will not contain any kind of cycles. So that should be called as a acyclic graph. And breadth first search and depth first search on the same graph do not give the same order of the vertices. And next one, so the order of visiting vertices depends on the node where we are going to be select the first, and hence the order of visiting nodes may not be depth first search. So depth first search is similar to the in-order traversal of the tree, and the stack is going to be used to implement the depth first search. And depth first search follows the following rules. So select an unvisited node X, visit it and treat it as the current. Okay. Select an unvisited node X, visit it and treat it as the current. Find an unvisited adjacent of the current node Y, visit it and make it as the current. So repeat the steps 1 and 2 till there is a dead end. Means that so vertex U does not have some nodes and no more weights nodes can be visited. So after coming to the dead end, so again have to perform the black tracking along with parent and see whether it is going to have under adjacent vertices other than Y, and repeat the steps 1 to 3. So DFS is similar and not the traversal of the tree, and stack is going to be used to implement the depth first search. So for the depth first search, you can going to have the graph. So if you want to implement the depth first search, I have to make use of this stack data structure. So DFS rule should be as follows. So select an unvisited node X. Select an unvisited node X and treat it as a current node. So this one is going to be treated as a current node. And find an unvisited adjacent to current node of Y. So whatever vertices that are adjacent to B. So that means I have to P top of A and push B onto that. So what are the vertices that are adjacent to B? C. So top out and push C onto this. What are the adjacent vertices that are connected to B? So top out C and again top out. And this should be the DFS order of this tree. So like this, we are going to be construct the DFS graph graph here. Okay. So after communicating with that end, so they are going to do one more separately and then perform that. So here a stack can be used to maintain the track of all the paths, and initially I'm going to be a vertex that should be pushed onto the stack. And to visit the vertex, we are going to pop vertex from the stack and push all the vertices onto it. And the list is going to maintain to store the vertices. So that means the which is already visited one, and the vertex is will be popped out where the already visited are not can be known by searching the list. And if vertex is already visited, then you can able to simply ignore it and then have to pop the step from the next vertex to be visited. And this procedure is going to be continued until the stack is not going to be empty one. Okay, so depth first search means, so I'm going to have the graph line once again. C and D. So for the first step is that, so push A onto the stack. So this is the step 1 and step 2. So what are the vertices that are adjacent to A and C, B and C? So these two things are going to push on it, and A should be popped out. So this B should be A. And for B, what are the adjacent vertices? C and then D. So C is already there. So for C, what are the vertices that are adjacent? C is going to be popped out. B and then D. So D. And then D should be popped out. B and then C. So A should be popped out and B should be popped out. This should be the resultant DFS order of the tree. Okay. So for implementing this DFS breadth first search, we're going to maintain the stack data structure that is going to maintain the track of all the paths. So initialize the starting vector that should be pushed onto the stack. And to visit the vertex, we're going to be pop the vertex on the stack and push all the adjacent vertices onto it. And the vertex is going to maintain popped out, so whether it is already visited or not. And if the vertex is already visited, then you can able to simply ignore it and then you can able to pursue the same thing until the stack is going to be empty. And we're going to have the breadth first search. So breadth first search is almost all similar to the pre-order travels of the binary tree. So the breadth first search of the graph is similar to the traversing the binary tree level by level. So that means visiting all the nodes at each level from left to right, and all the nodes at any level should be i+1. To implement the breadth first search, we are going to use the queue data structure. So select an unvisited node X, visit it, and have that the route in BFS order. And from each node X in the current level, visit all the unvisited neighbors of X. And repeat the step 2 until no more nodes can be visited. And if there are still unvisited nodes, repeat from step. So okay, so the breadth first search is almost all similar to the post-order traversal of the binary tree. So there should be different traversals of binary tree like in order, pre-order, and post-order. So if I'm going to have a binary tree like this, so in order should be BAC, pre-order should be ABC, and post-order should be BCA. So the breadth first is also similar to the post-order traversal. The post-order traversal of the graph is similar to the traversing binary tree by level, and all the nodes at any level. So visiting before the nodes. So implement this binary search, we're going to use the QS data structure. So how this one is going to be implemented here is that, so select an unvisited node X, okay, and then visit it by putting the root in various BFS tree. Then level is called current level, and from each node X in the current level, so visit all unvisited neighbors of X. So repeat the step 2 until no more visited nodes are going to be visited, and if there are still unvisited nodes, so repeat from step 1. So let us consider the graph how this one is going to be implemented. So for this I'm going to take step Q. So first one I'm going to consider as A. So pop out, and BFS is A. So whatever the vertices that are adjacent to B, A is B and C. So BC. So for B, C is already there. For C, let us consider C and D also. C and finally D. So like this we are going to be considered. So if I'm going to tree level, so A, B, C, and then D level by level. So let us consider an example here. So how we're going to construct the BFS and DFS. So this is the real-time graph. So for this one, so the DFS is going to be find out. So for this, I'm going to use the stack data structure. So initially, I'm going to take A, and A should be popped out. So what are the vertices that are adjacent to A, B, and D? So I'm going to consider B should be pushed onto the stack. So what are the vertices that are going to be there, and B and E is there. So pop out and push E here. So what are the vertices that are adjacent to E, D? So A should be popped out, and D should be there. So for D, C should be there, and finally C. So this should be the resulting order of the DFS. And then next one, breadth first search order of this. So what is this breadth first search? So for this, I'm going to make use of Q data structure. So Q means that, so I'm going to consider A. So what are the elements that are adjacent to, A is that B, C, D. So remove the Q, add it to BFS. Then B, E is there, E. So C, E and D already there, D already there, E. So this order is different and this order is different. So but the traversing is same. So if we look at this depth first search, so the graph looks like the tree A, B, C, D, and then E. Whereas this one, so breadth first search, it should be A, C, B, C, D, and then D to E. So so let us consider another graph here. So in this graph, what I'm going to say is, so find out the DFS and breadth first search order. So in DFS order, I have to make use of the stack. So then first visiting node is A, from this B, and from B to C, and C to F, and F to E, E to G, G to D, H. This should be the DFS order. When it comes to breadth first search, so breadth first search is different. So first I'm going to use for A, it should be B, E, and then D. Okay. Then I'm going to consider next level is C, G. And next level HAF, and then I. So the structure is different in this case and in this case. Okay. So the DFS on BFS order is something different in this case. So here I'm going to make use of the stack data structure. Here I'm going to make use of queue data structure. So find out this breadth first search and DFS of this. So what should be the DFS order of this one? So breadth first search means that I have to visit level by level of the tree, visits of the nodes. So that should be the breadth first search. So that's why I'm going to consider V1, V2, V8, and V3. So this level I visited. Next level is V4, and next level is V5, V6, and next level is V7. So like this, I can simply draw this BFS order of this graph. And DFS means that, so here I have to visit level by level. So first I'm going to consider V1, V2, V5, V7, V4, and V8. Again, I have to come to backtracking, V6 and V3. So when it comes to the applications of the graph, so we're going to mainly use this graph in electronic circuits, where we're going to be used in printed circuit boards and integrated circuit, whereas the graphs also going to be used in transportation network like highway network and flight network, and whereas this graph also going to be used in computer networks like local area network, internet and web, and database. It should be represented as entity relation diagram. So these are the various applications of the graph, so which is going to play real-time applications. So in electronic circuits, we're going to use the circuit board and integrated circuit, and transportation means highway network and the flight network as well, and then computer networks like local area, internet and web, and entity relationship in case of database. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.